In this video, we are going to talk about electrophilic aromatic substitutions in substituted benzenes. Okay? In substituted benzene. Common substituents like OH minus, or NH2, maybe an alkyl group or a carbonyl. Okay, these are some of the common substituents that are found. They can either increase the electron density of the ring, or they can decrease the electron density. So groups which can increase the electron density are called as activators. Okay, so they will be called as activators, and groups which decrease the electron density, they are called as deactivators. So for example, if you have a benzene that is substituted with an alkyl group, if you want to bring another substituent onto this already substituted benzene, so for example, I would like to do halogenation here, Br2 with AlBr3. These are the reagents that are needed for halogenation, and if you recall from our previous video, the electrophile that we are going to look is Br+, right? The alkyl group directs the incoming group to either the ortho position, so the Br will occupy the ortho position, or it will occupy the para position with respect to the R group. We do not see products where the Br is substituted anytime at the meta position when we have the alkyl group as my first substituent. So let's quickly do a review of our ortho, meta, and para positions. So here is my benzene. If I have a substituent here, then these positions with respect to the substituent are ortho. These substituents over here, these positions over here are called as meta, and this is called as the para. Okay, so 1, 2 is ortho, 1, 3 is meta, and 1, 4 is para. Okay, so coming back to this example here, when you have an alkyl group, it directs the incoming electrophile, which is this one, to either to the ortho position or to the para. We do not see products where the Br is substituted at the meta position. On the other hand, if you have a benzene ring that is substituted with, say, for example, NO2, okay, and we do perform the same reaction again, treat it with Br2 and AlBr3, this generates again my electrophile, which is Br+, correct? So Br+ is my new electrophile. However, unlike the case before, where the alkyl group was directing the new electrophile either to the ortho or para position, here NO2 directs the electrophile to the meta position. Okay, so our major product here is where the Br is in the meta position. We have small amount maybe of ortho and para, but major product is meta, by which we can conclude that there are certain groups which are ortho and para directors, and there are certain ones which are meta directors. And it's always the groups which increase the electron density onto the benzene ring that direct the incoming group to an ortho or para positions. Okay, so that means we can say that activators are ortho and para directors. So anytime you have a group that is an activator, it will direct the incoming group to either ortho or para position. Okay, sometimes we'll get both. Okay, and then deactivators are the ones which are meta directors, the ones that decrease the electron density of the benzene ring. Okay, so activators increase electron density and they bring the incoming group either to the ortho or para position, sometimes both. We get a mixture of both products. And deactivators, which decrease the electron density, they direct the incoming group to the meta position. So we have in our textbook this table which tells us which are the groups which are meta directors and which are the ortho and para directors. Okay, so these groups which are represented in blue, they are all deactivators. Okay, so these are all deactivators, whereas the red ones here, the pink ones, they are my activators. Now in between we have halogens which are actually deactivators. However, they direct the incoming group either to the ortho or para position. Okay, so how do we know, like, what is the reason that a deactivator will direct the incoming group to a meta position and activator to the ortho and para position? This can be actually explained by two effects. We call it as the inductive effect, and second one is the resonance effect. Because groups can increase the electron density or decrease the electron density by both these factors. Okay, so for example, to illustrate this, if I have an NH2 group, okay, so if I have NH2 group, which if you look, it's a activator or an ortho or para director. Okay, this NH2 group can form resonance structures where the pair of electrons on nitrogen can form a double bond here, at the same time break open this pi bond, and you can get a resonance structure where the negative charge is on this carbon atom and we have a double bond to this NH2, making this nitrogen positively charged. Okay, you can continue this delocalization of this pair of electrons onto the other carbon atoms of the ring. So you can move this pair of electrons here now and keep the nitrogen with positive charge intact, or you can move it here on this side of the ring where you have the negative charge now on this carbon atom. Okay, now if you see, this is an example of a resonance effect because NH2 group donates electron density to the benzene ring through resonance, right? It is donating the electron density. It's increasing the electron density on the ring by resonance effect. And the ones which increase electron density are ortho and para directors. And we can also say that they are ortho and para directors because you see the negative charge is residing at the ortho position and at the para position, right? See here it is at the ortho, the negative charge goes to the para and then back again to the ortho. So that means if you have an incoming electrophile which is positively charged, where do you think it would like to go? It would either go to ortho positions or to the para positions, right? Because positively charged species will like to go to the where it is electron rich. So that's why activators can be ortho or para directors. Okay, you can take the example of OH, a molecule like OH group. sorry, but if you take an example of a benzene ring with OH here, you can again do the same thing as we did with NH2, or you can also, so let's draw the first one. Okay, so what we talked about NH2, that here again a pair of electrons can form a double bond, and you can break open this pi bond, resulting in several resonance structures. Okay, here where the pair of electrons are residing on this carbon atom, oxygen has a double bond with a positive charge, right? And then you can move this pair of electrons as we did in the previous example of NH2, where the electrons can move over to this carbon atom and then over to the carbon atom on this side. Okay. So if you look again, it's similar to the previous example where the negative charge is concentrated on the ortho and para position, so the incoming electrophile would prefer to go to the ortho or para position. And if you go back to this page here, see, OH is also a ortho para director. Okay, so resonance can help us to explain the ortho and para directing effects of OH or NH2 type of groups. There is another way we can explain this effect is by assuming that, say, we have a new group NO2 that can take up either the ortho, the meta, or the para position. Okay, so we already know that OH is a ortho para director, so we will not get any meta products. However, let's look at the reason, another reason why we will not get any meta products, only ortho and para. So if you draw the sigma complex where the NO2 has taken the ortho position, you will see that we have a positive charge on the sigma complex that's formed at this carbon atom, which can be resonance stabilized in this form. Okay, like we did in the reactions where we formed the sigma complex earlier. Now, when it does when the reaction happens with the NO2 at the meta position, you can see that the positive charge is here. Okay, and we have only 3 resonance structures here. If the NO2 or the new incoming group goes to the para position, then again we result in 4 resonance structures of the sigma complex. So greater the number of resonance structures, more stable the compound is, right? Or the complex is. So we see that when the NO2 group or any incoming group, we can say any incoming group goes to either the ortho or the para position, we have more resonance structures. We have 1, 2, 3, 4. Same with para, we have 1, 2, 3, 4, which stabilizes the molecule more, rather than in case of a meta attack, when the incoming group goes to the meta position, the sigma complex is stabilized only by 3 structures. So this also adds to the fact that OH, groups like OH or NH2 or ethers, aryls and alkyls, they are ortho and para directors because they activate the ring by resonance effect. Okay, if you look at CH3, which is this example here, alkyl group here. Okay, one way of explaining why CH3 would be ortho or para director is slightly different from what we explained for OH when we had an OH or an NH2 group at this position. Okay, so if you look, when we have a methyl group, and again we look at the scenario where the new incoming group is either at the ortho, meta, or para position. Okay, we are assuming that at this time we do not know where the NO2 group or the incoming group will go. So we will look at all the 3 scenarios where the NO2 is in the ortho position, it's in the meta position, and in the para position, and we get the sigma complex. Okay, so if you look at, this is the first sigma complex when the reaction happens at the ortho position, or the NO2 takes the ortho position. We can see that CH3 is a electron donating group. Okay, it donates electron density by inductive effect. So it stabilizes this positive charge in the structure, right? Same thing happens with para. If you look at, there are 3 resonance structures for the sigma complex, and in one of the structures, the positive charge is very close to the methyl group, and methyl group is electron donating via inductive effect, so it stabilizes this positive charge. However, when the NO2 group is at the meta position, in none of the sigma complexes, the positive charge is close to the CH3, right? It's either here, here, or here. However, it is not close to the CH3, unlike the ortho and para positions. So the positive charge does not get as stabilized as in the ortho and para positions. Therefore, the incoming group being in the ortho or para positions with respect to CH3 is more preferred than the incoming group going to the meta position. You can see that we have 63% of this, 34% of this, and only 3% of the meta being formed, and this could also be given as an additional reason to explain that. Okay. If you look at a meta director, okay, so going back to the page where we looked at some meta directors here, right? So all these ones in blue, they are the meta directors. If you take an example of that, we can see that why this groups like CHO or carboxylic acids, they are meta directors. Okay, so similar to the previous example, we will take a scenario where the incoming group is either going to the ortho, meta, or para, assuming that again we do not know what is the directing effect of this aldehyde group. So we react it with HNO3 and H2SO4, resulting in an NO2 electrophile, which can either go to the ortho, meta, or para. However, when you look at when the NO2 goes to the ortho position or to the para position, the positive charge resides at a carbon atom which is very close to this carbon atom which has a positive charge, right? And how do we get the positive charge? Because oxygen here, the carbon-oxygen bond is a polar, so oxygen gets a negative charge and this carbon is positively charged. So we have seen a scenario where 2 positive charges are close to each other. Same thing with para. If the NO2 attacks the para position, then we have one of the resonance structures of the sigma complex where the positive charge is again close to the positive charge of the other carbon atom. So this is a state of instability, least stable, because 2 positive charges are close to each other. Same thing here. See, 2 positive charges are close to each other. But on the other hand, when the NO2 group goes to the meta position and we look at the sigma complex, we do not have any resonance structures where the positive charge is close to the carbon atom, right? It is over here, it's over here, and it's over here, but it never comes close to the carbon atom, which which is next to the aldehyde carbon. Okay, so we do not have a destabilizing resonance structure in case of a meta, whereas in case of ortho and para, we do have a resonance structures that is less stable. So the CHO becomes a meta director because it has more stable resonance structures in this case. So these are the different ways by which you can explain the directing effects of different groups. Okay. Now halogens, if you go back to this page and see halogens are an exception. They are deactivators by inductive effect. However, because they are electronegative, so they kind of drain out the electron density from the benzene rings, they're deactivators, but they are ortho and para directors by the phenomena of resonance. Okay, so if you look at chlorine, okay, we have a halogen substituted, and we again look at the case where NO2 can either go to the ortho, to the meta, or para. Okay, here we are just taking an example of NO2. It doesn't mean that we only have substitution by NO2. We can also have bromine, we can have sulfonyl group, we can have alkyl group, okay? But this is in general explaining that in case an incoming electrophile goes to the ortho, the meta, or to the para position, how do we decide which one would be the best positions, which one would be the best position for the new substituent to take? So we look at a case where NO2 goes to the ortho, and now our existing substituent is a halogen, chloride. Chloride can do it pulls electron density out by inductive effect, but at the same time it can make the the benzene ring electron rich by pushing back the electrons towards it. Okay, so for example, it can form a double bond here, and then it can we can look at a structure where again you see that we have an extra structure out of the different resonance structures which stabilizes the molecule. Okay, same thing with para. See, we have 1, 2, 3, 4 resonance structures when the NO2 goes to the ortho, or when NO2 goes to the para again, we have 1, 2, 3, 4. We have an extra resonance structure helping to stabilize the sigma complex. Whereas when it is at the meta position, you see that we have only 3 resonance structures. So comparatively, it should be preferring the ortho or para position because of the extra stable resonance structure that is available. So that is why halogens are ortho and para directors, even though they are deactivators. Okay, so I hope this makes sense about the directing effects. Okay, you will be given this data table regarding the activators and deactivators, but you should be able to explain why these groups are activators or deactivators in terms of either resonance effect or inductive effect. Okay. Application wise, we will look at some synthesis problems where we will take benzene and convert it into different end products, but which substituent should go first during that synthesis process is very important. Okay, so we will talk about that in the next video.